It is 12:01. Good afternoon, everybody, and thank you for joining. I'm Anna Plotkin. I'm Director of Continuous Professional Development at the University of Toronto, Department of Laboratory Medicine and Pathobiology. And I'm really thrilled to invite you to this absolutely new, amazing opportunity, new community of interest of optical genome mapping. This is really a huge part on Adam Smith's work, and Adam will introduce the new community and he will chair that community now and in the future. Adam?
Thanks very much, Anna. So it's a pleasure to be able to get everybody together, and hopefully we'll be able to keep this community of interest going over the next few years and have regular meetings. So this is a partnership of sorts with the CCMG as well, so our CCMG community of practice. And the really nice, part, I think, for those of us that collect CME credits is that as long as you fill out the survey after the event, you get a nice certificate accrediting that you've spent this time doing a accredited learning activity by the Royal College, which is great for all of us to keep keep in our main port continuing education profiles. So I really I wanted to do a few things during this meeting. Obviously, we are going to have a presentation, which I'm going to give to sort of kick off the series, talking a little bit about acute myeloid leukemia testing and talking about a Canadian-specific region file. And so we're going to do that. We want to have some time for discussion about that as well. So we'll reserve some time after that for discussion. And of course, in addition to that, we have several case presentations this afternoon as well. So just short 5 to 10 minute case presentations where people can show and share interesting data and get some conversation going with everybody. So that's the general plan for the afternoon or morning, depending on which time zone you're in. And we really hope that everybody enjoys the meeting. Please use the chat function to send questions and comments. I think, and I might have to confirm with Jenny about whether or not people can access their microphones or not. I'm not 100% sure how we've set that up for this webinar.
Yeah,
so, but
it's an open meeting. Anybody can speak.
Great. Okay, so if you do have questions and you want to speak up, just speak up. Raise your hand, and we'll take questions and comments and discussion in order. Okay. I also wanted to also thank Eric McGuinness and José Lavoie, who are co-chairs of the CCMG COP with me, and all of you for your participation. So I think we have a good number of people signed on. We have, it looks like about 69 people signed on. So we're gonna start this first presentation, and then we'll go into the discussion from there. Okay. So I think as many of you probably know, we've been working at UHN for a while in terms of validating myeloid applications and specifically acute myeloid leukemia testing. And one of the key issues, of course, that we're interested in is the use of our myeloid gene file or region file. And I think this is something that we're, I would certainly like to discuss more as a group, and hopefully reach some kind of national consensus on a region file. So we've got a pretty good start here. And so I'll go through a sort of general introduction and just sort of talk about the general approach we take to analysis in acute myeloid leukemia, talk about a region file or reporting templates. And then I think, have some discussion at that point about where it is we should probably be looking at going. Okay, so generally, this is sort of the overview for the presentation. as a whole. We've got the analysis steps that we take. So I'm going to take a quick moment. I'm going to review filter settings. I'm going to talk a little bit about variant analysis, enumerating cytogenetically visible variants, in vis-a-vis towards being able to sort of map OGM data back to cytogenetic complexity, talk about filtering using a gene or region specific file. This is a bed file basically that you upload into Access, classifying obviously using the 4-tier system, and reporting. So this is basically a table of filter settings that we use for analysis. So if you are, obviously, if you're not terribly familiar with using the Access software, this won't mean a whole hell of a lot to you. But again, if you are more familiar with the software, this is, of course, you'll probably recognize most of these settings. And if you pull up the filter settings on Access, these are the tabs across the top. And then these are basically how we set the filter settings. And so I think most of this is pretty standard for BioNano as well. They recommend sort of generally these filter settings. The big difference, I think, for us and for most of the groups internationally that we've been working with is that we actually recommend going to all structural variants for SV masking filter, and the same thing for the copy number variant masking filter, we go to all copy number variants. And then what we do is we set the control value for the variant annotation filters at 1%. And so what this does is this uses the control database. So remember, as you may know, there's a 300 sample control database, which has all the examples of all sorts of different kinds of common population structural variations. And so what this does is this basically says that all the really common structural variation, anything seen in 2% or more of the population, we're just going to filter that out because that's common structural variation and we don't really want to see it. But it does allow us to see some of the structural variation that occurs in masked regions. And a lot of times, you know, this is stuff near centromeres, and it can be, you know, it might be, these might be false calls, artifactual calls. But it's really good to actually, we feel, to look at that data and discard it based on the criteria for variant analysis, rather than not see it, not know that it's there, and that it may be something important. So that's why we've sort of selected this this type of filter settings. We set the copy number variant minimum size at 500,000 base pairs for the copy number caller. Of course, SVs will call down to 5 kilobases in the rare variant assembly. Okay, and again, aneuploidy confidence set to recommended. And so just to make a comment both about the copy number confidence for recommended and the aneuploidy confidence for recommended, we do find that both of these settings are really quite stringent. And so it's quite common that if you go to the genome view in the software and you look at the copy number across the chromosomes, you can see quite noticeable deflections, which indicate you know, a copy number change. And sometimes, depending on the percent of cancer cells in a particular sample, may not be quite high enough to hit the threshold for the confidence for these settings to make a call. However, if it is visible and you feel confident in evaluating the data manually, you can actually switch the filter setting to all. And of course, this will help you, this will allow the software to make the call that you're visually seeing. So this entails sort of a manual inspection of the data, which is also fairly commonly done in microarray cases as well. And so that's pretty much what we have for filter settings. I just wanted to make this point here about filter settings is that once you start customizing your filter settings, so once you move them away from the recommended settings in your instance of access that you're using, you will take those filter settings across all samples. So if you start playing with custom filter settings, just remember when you move into a new sample and you want to do analysis again, really what you should do is reset filters. There's a little button to reset the filters, reset them back to the BioNano default values, and then reset them up. There's a few clicks you have to make basically to reset these, like resetting these values here and changing to all structural variants and all copy number variants, just in order to bring you back to a default setting. One of the comments we've actually made with BioNano is on that little window with the filter settings where it has, reset filter settings, and we've actually asked them to add a button that is custom setting, or saved settings, or whatever they want to call it. So what you're going to be able to do is set this up, save it, and then whenever you will go into new sample, you'll just click the button and it'll actually bring you back to your default settings. So we should hopefully see that in version 1.8 of Access, which is the next version. Okay, so we have established criteria for reviewing different classes of variants. And for those of you that participated in May in the user group meeting that was in Toronto or online, we did talk about this in more detail. So I'm going to do a very sort of quick recap of this, and then we'll go, into some examples. So there are basically three classes of structural variation that we're going to look at whenever we're looking at any case using optical genome mapping. So we're going to look for intra and interchromosomal fusions. So these are generally large changes, segment exchanges between chromosomes, either homologous or non-homologous. And so these are classically are translocations, insertions, or inversions. And I say large insertions because insertions have to reach a certain size threshold to be definitively called an insertion with a recipient and a donor. And I believe in the RVA, the size is about 70 kilobases. And so you need enough sequence and enough labels for the software to be able to map that label pattern back to the appropriate place in the genome where it comes from. Below that level, you can still get a call for an insertion, but it'll be insertion ? And that just means that there aren't enough labels, or it's not big enough for the software to be able to map it back to where it comes from. So you will see those two different types. Second category is our unbalanced SV calls, and these are called by the SV algorithm. So you'll see deletions, duplications, and insertions. And so this covers the sort of window below 500 kilobase pairs. I mean, they can be larger than this, obviously, but just to differentiate from the large CNA calls. So again, anything here, you're going to see these small calls called by the SV algorithm. These won't be called by the copy number algorithm. So you get your large CNA calls. We've normally in the software set the threshold at 500 kilobases for this. And of course, aneuploidies at the whole chromosome level. Again, we can often see these two types of abnormalities overlapping. So you'll see an unbalanced SV call, like a deletion, let's say a 5q deletion. You'll also see that called by the copy number. So you get those two pieces of evidence together that, very clearly allow you to make a confident call. But sometimes, depending on the size, depending on where a particular region starts and stops, like for example, if you had an isochromosome where it's, there's no sort of link from one piece to the other piece, you just lost the P arm and duplicated the Q arm, you'll actually only see a large CNA call for those. And so you can see large CNA calls that don't have SV calls with them. That routinely happens depending on the type of abnormality. Okay, so again, quickly just to go through the intrachromosomal fusions. Again, we want to make these calls based on 5% or greater allele burden supported. So that's VAF, supported by greater than or equal to 10 molecules. And then of that, on the actual map itself, we want to have at least 10 labels on either side of the breakpoint to provide strong evidence for positive call. We also have a look at the confidence score. The confidence score goes between 0 or -1 in some cases, up to 1 or 100%, which would be very confident. Confidence score is a guide. It's not the be all and end all. If you have a very real looking, rearrangement with a low confidence score, it can still quite possibly be real, given that it meets all the other criteria. Remembering that confidence score is based on modeling, and so in some regions of the genome where there might be lots of repetitive sequences or close to the ends of the chromosomes, sometimes the confidence levels will fall on particular calls. So question for Jing: with the PowerPoint slides made available? Yes, we can certainly distribute a PDF afterwards, and also the session is being recorded, so you can go back and watch it later if you want as well. And Juyun asked, do you know what happens to specificity when you go down to 5 molecules? 5. So yeah. So again, what we're talking about here, Juyun, is we're talking about a rare variant analysis with a data capture at about 1,500 gigabase pairs. Now, we can actually set that target higher. So 1,500 gigabase pairs gives you about 300 to 400x genome coverage. So we can actually hit that. We can actually bump that up, and we can get more coverage. So, again, if you're to go down to 5 molecules, we've said like between 5 to 10 molecules, we've sort of called this a gray zone. And you have to remember, of course, that when you have samples with varying amounts of cancer cell fractions, you can actually get very real calls down to 5 molecules. Normally in the software below 5 molecules, the software will not show you those calls. That's actually a setting in the software, but you can actually go into the filter settings again, and you can take that specific setting and you can set it to 0 and have it show you anything. Just like with the filter level settings for intra and intrachromosomal fusions, and other types of abnormalities, they're set at the recommended levels based on their confidence scores, but you can actually turn all of that off or on, depending on the way you want to look at it. You can set the confidence to all, which will give you absolutely everything, even the very low confidence stuff. So there is a lot of flexibility in the software to do that. I mean, I think the question, specificity, we've looked at doing in silico dilutions of a sample with a lot of abnormalities down to very low levels, down to about 3%, 0.03. So, and we can see the calls drop proportionally with each serial dilution or in silico dilution that we do. So it's actually very, the system is very robust. And again, if the data and the calls look good, they're probably real. The big question is, when we get sort of down around VAFs of 5% and, between 5 to 10 molecules, this is really low level. This is at the limit of detection. So anything that we would see at that level, we want to be very careful about reporting and probably put some kind of caveat on that you know, this is at the limit of detection, much like we would do, say, for example, in a fish assay. If you had a positive result at the limit of detection, you would say, you know, hey, look, this is positive, you know, by the numbers, but it's at the limit of detection, so just keep that in mind. So sorry, that was a very long answer to that question, but I hope that helped. Also, we've looked at a lot of SV calls that are artifactual, and some of these can have very high VAFs. They can have more than 10 molecules. Often, a lot of these calls will have 10 or fewer labels that align on one side of the breakpoint. So there's a lot of repetitive sequence in the genome, as you all know, and of course, you'll get these very similar label patterns that will occur, and sometimes the software will try to make that call. You know, what we would recommend in these cases is you look at that, you look at both sides of the alignment, you look for features, like seg dupes and gaps and other features in the reference genome that might cause there to be alignments, and also look at the label pattern itself and see if it is in fact repeated. There's lots of ways that we can go through the data to actually look at it and determine whether or not we feel that it's a valid call, a non-artifactual call. Right, I believe that's a repeat. With an interchromosomal rearrangement, it is important to determine if it's balanced or unbalanced. And so normally we can see this by having two maps, so that one map relates to the one derivative chromosome and the other map will be to the other derivative chromosome. You know, you can do this just by going through each of the calls and looking at the maps using the show all function. And so if it's not balanced, if there's only one call, then often we would expect with that to see some kind of imbalance in copy number. And so that's one of the ways that you know, it's usually easy to tell whether or not you've got a balanced or an imbalanced rearrangement, because you can see changes in copy number at the breakpoints. So Ashish asks, how does pseudogene versus gene mapping occur in SV or CNA calling? Again, so that's a very sort of gene level question, and you have to remember that the label spacing is you know, roughly about every 6,000 base pairs. So we're really like a label, depending on the region, you know, you've got a few labels overlapping a gene, but genes and pseudogenes will have different overall label patterns, and so you'll be able to differentiate the different regions by the fact that locally their label patterns will be different, even though the gene sequence might be very similar. Okay, moving on. Unbalanced SVs less than 500 kb. So SV calls observed at 5% or greater allele burden supported by greater than 10 molecules are likely real. SV confidence score may be used, but just remember, you know, again, my comment about the genome context here, and that confidence scores are not actually calculated for duplications. They're always -1, so just don't let that give you pause. And then the confidence for deletions and insertions is also set to 0 in the recommended filter settings. So you're actually pretty much, for most of these, you're seeing everything that the software is calling. The software is actually really quite confident at calling these types of events, whereas the interchromosomal stuff is a little bit more complicated. And so one of the problems we do run into are the false positive calls or artifact calls that we see in regions with segmental duplications and or palindromic sequences. So, you know, this is problematic because some of these calls may look a little bit like false calls. They might actually be real because of the fact that segmental duplications do have a tendency to to have non-allelic homologous recombination, and so they end up, you know, copying or deleting themselves just as a sort of natural function. And so you can actually have differences in a lot of samples between these regions and the reference genome that you're using. So anyways, and in the alignment process, there's this pairing of non-unique map segments to an incorrect LCR further away, and that's basically what happens. And we can sometimes see artifactual inversions or inverted duplications in areas of the reference where there's a palindromic type of sequence, where it's the same pattern of labels on either side of a particular region. And so this can sometimes give a little bit of difficulty to the assembly. So these are just sort of things that you have to keep in mind when you're looking at a lot of this stuff. And so this is where things get a little bit more challenging on the cyto side, because we want to try to make OGM as close to a sort of a karyotype result as we can, so that we can use the karyotype derived classifications. And so we followed the McHale et al. 2019 array guidelines for 5 megabases as the cutoff for size for cytogenetically visible. I know many of you, we've had this argument. It's a huge argument. I think I probably brought it up before. What is actually cytogenetically visible on a bone marrow karyotype? 5 megabases is euphorically optimistic. We sort of said, 10 megabases is probably normal, or you're probably getting into a range where you can actually see it. And we know that depending on the quality and banding and morphology and everything else, that even in some regions of chromosomes, somewhere between 20 and 30 megabases might even be truthful numbers as well. But in order to try to keep what we do as consistent across methodologies as possible, we've opted to go for this 5 megabase cutoff. For intra and interchromosomal rearrangements, any cytogenetically visible or balanced or unbalanced intra or interchromosomal arrangement should be counted when you're trying to ascertain how many rearrangements there are. This includes both disease-specific recurrent translocations, but also other rearrangements that would be detected by CBA that are somatic. And that's sometimes a challenge, but we'll talk about that later. And note that while cryptic translocations would not be counted by CBA, as they're obviously invisible, they should be counted by OGM. So, we're trying to as accurately as possible enumerate the cytogenetic abnormalities that are seen, whether they're actually visible by G banding or not. So we know there's a lot of cryptic translocations that we're not seeing by G banding, that we routinely fish for. The T1221 and BALL, for example, would be a good example. Sorry. Question from Arun: Can gene pick up jumping translocations? So yes, it should be able to if they occur outside of the centromeres. If the translocation breakpoints are in the centromere, so if they're whole arm unbalanced, or they involve, which they often do, the acrocentric P arms, then it may not. However, what you will see quite often is the copy number consequence. So you'll see the copy number caller, probably like for the prototypic example would be increased 1Q. So you'll see the entire segment for 1Q increased by the copy number algorithm, and that will give you the clue that that there's probably some unbalanced rearrangement involved in 1Q that's going on. Okay, so just to wrap this up, so catastrophic genome events is something that you're going to see with a bit more clarity on OGM. So all the chromoanagenesis stuff, which includes chromothripsis, chromoanasynthesis, and chromoplexy. And so chromoplexy, we've seen a few of those. They're actually quite nice. That's the one that's quite kind of easy, I think, to pick out. I find chromothripsis and chromoanasynthesis can be a little bit more challenging sometimes to tell them apart. It depends exactly how you define them, it's not always clear. I mean, I think the big thing is that there's no rule in cell biology that says you can't have one and not the other, or you can't have chromothripsis and then a bunch of other changes that make it sort of more challenging to sort of tell the difference between the two. So for most of these, certainly for these events, not so much for chromoplexy, because we can usually it's cleaner, you can pull out what's going on here, but for these, we quite often just use the CX complex genome nomenclature for these. And so recurrent clinically significant copy number changes, hyperdiploidy, IM21, of course, these are things that we want to try to talk about as much as we can. Okay, or identify them in the report. So having said that, this is our general approach to analysis. We start with an assessment for large cytogenetic abnormalities. And so just basically, these are the rules that we've just gone over in the slides before. Then we move down to discussing copy number abnormalities from 500 kb to 5 megabases. So these are the ones that aren't going to be included in a genome complexity score, but are going to be important possibly nonetheless. And then, you know, there are some really pressing questions here, like, you know, how small is a 5q deletion? How small is a 7q deletion or a 20q deletion, et cetera? So I think those are kind of interesting, sort of potentially interesting to discuss. And then for smaller SVs, this is where we use a region file. And we can also look for very small SV abnormalities that are important for reporting. So just to give a couple of quick examples here, here's a circus plot showing an 11p deletion here. So you can see there's a fusion call here joining these two segments on the P arm, and then the copy number call there as well. So there's a deletion from P1 4.3 to P1 1.2. So we've got a large 21.2 megabase deletion on 11p. We move to our next level, which is we assess for copy number abnormalities from 500 kb to 5 megabases. The copy number track is pretty clean, so we don't see any additional copy number abnormalities. And then we go to small SVs, and this is where we apply a myeloid region file. And this allows us to sort of pick out these relevant SVs very, very quickly. So what it identifies right away is we have a KMT2A partial tandem duplication. We've got a couple of other mechanisms here. So we've got this abnormality here with bin2. So bin2 is in our region file, but it's designated as a partner of fusions. So this is not the correct mechanism. And in fact, again, VAFs here very close to 0.5 in both cases. So we've actually, these are probably most likely tier 4 abnormalities. They're present in the person constitutionally. Again, same thing here with this insertion, distal to GLIS2. GLIS2 is a fusion partner generally, so incorrect mechanism not reported. And then up here at RUNX1, so this is actually an interesting abnormality because it's a tandem duplication of RUNX1. RUNX1 we have classified as a gene that both undergoes fusions and loss of function. So if we look for sort of tandem duplications inside RUNX1, what do we see? And we don't really see anything from sort of PubMed searching or looking in CKB Boost. No sort of large tandem internal duplications of RUNX1 as a recurrent phenomenon. That being said, nobody's really looking for these, so this might be something we need to follow because it could be something that becomes more apparent as we do more of these. The size of this duplication here is 36 kilobases, so you can see it. This is the exon structure for RUNX1 transcribed in the minus direction, so it's overlapping a couple of exons here. So, and maybe exons that are not in all the transcripts, so who knows exactly what that is. Again, so we're going to call that tier 3 unknown significance. Question from Nassim about how to choose the regions file for the myeloid bed file. Good question, which I'm going to get to on the region file slide in a couple minutes. Okay, so here's another example I just wanted to show this example because I think it's really interesting and sort of the stuff that we're seeing when we're looking in more detail. What you can see when you look at this, again, copy number, fairly consistent. There looks like there's maybe a little bit of Y chromosome loss. And then there is a translocation 2-4 here. So again, this is cytogenetically visible. We did the karyotype on this. We saw the T24. If we'd only done the karyotype, that's all we would have known. So again, we then want to look at copy number abnormalities from 500 kilobases to 5 megabases. And in fact, when we look at the breakpoints of this translocation, you can actually see that there's a telomeric breakpoint and a centromeric breakpoint for each of the translocations, for each of the derivatives, and that the intervening sequence between these breakpoints is deleted. And in fact, if you look inside the deleted region, you can see that DNMT3A is inside the deleted region on 2, and these are the maps here that showing the translocation breakpoints in the hybrid maps 2-4 and 4-2. And then again, this is the region on 4 deleting TET2. So this is just a super interesting case with deletion of DNMT3A and TET2 from an apparently balanced translocation 2-4. So again, showing the value of really getting into that, that lower resolution. And so again, if we look at 20q deletions, for example, one of the key, so here are some key criteria for categorizing AML patients. One is mutations in ASXL1, BCOR, etc., or the complex karyotype and or classic cytogenetic abnormalities associated with myelodysplasia-related MDS or AML, and of course the del20q. This particular case, and we have several of these as well, this actually has 2 deletions. You can see there's a deletion call here and a deletion call here, and they're different sizes. One is 617 kilobases, the other is 3.4 megabases. These are both invisible to classical cytogenetics or karyotyping, so they wouldn't be detected. And you can see that VAFs on these 2 calls, 0.3 and 0.41. So both too high for them to be the same deletion. They have to be on separate alleles. So the dual deletion involving ASXL1. So, I mean, this is actually really, really interesting. This actually moves this particular categorization from just a deletion 20q to mutated ASXL1. Although I'm not 100% sure how we're going to deal with some of these, because there are a lot of genes like EZH2, for example, that could potentially also be included in the category del7q. So I think there are some prickly issues around this that we're certainly just sort of going to have to figure out how to deal with, and we'll probably see updates to the classification as the amount of evidence around these types of submicroscopic cytogenetic abnormalities grow. So that's going to be very interesting and something that we're going to probably be talking a lot about in these meetings and in other meetings as well. So I'm not going to take too much time just to go over the 4-tier system. I think everybody's probably pretty familiar with it. Again, for us, we're reporting on our reports mainly tier 1 and tier 2 abnormalities. However, when we do look at overall genome complexity, we want to look at all the potential somatic abnormalities and add those up when they meet the criteria, so they're over 5 megabases, whether or not they're clinically significant structural variations or not. And again, tier 4 constitutionally benign, if you're comfortable making that call, we wouldn't include those in the count for complexity. Okay, and so just to sort of very quickly summarize our AML clinical validation. Again, I've showed some of this data before at other meetings, so if you've seen this before, just bear with me. So we've done a clinical validation of acute myeloid leukemia with OGM. We did it on 70 patients, most of them prospectively collected, although we did use some tissue bank samples to get some of the more rare patients. we found in that 70 patient cohort, by standard of care, if we add up all the karyotype and fish abnormalities, we detect 150 total abnormalities. By OGM, we detected 186 abnormalities that met the reporting criteria, of which I've discussed a lot today. Therefore, just looking at the increase in abnormalities detected, the overall diagnostic utility of OGM compared to standard of care is about 10% greater. So that is an interesting find. But what we thought was really interesting is, in fact, where OGM detected a tier 1 or a tier 2 biomarker that was missed by standard of care, and this is pretty much in a third of cases. And some of that has to do with the fact that the submicroscopic SVs, the stuff like the ASXL1 deletions, the B core deletions, those other kinds of deletions that we couldn't see with classical cytogenetics with karyotyping, we're able to detect those things because we just didn't have a way to do that before. And the other ones are largely cases where cryptic translocations were missed because they weren't cytogenetically visible. And so just graphically to illustrate that, this is basically how we classified the 70 cases by karyotype. We had 23% that were normal. We had 42% that had a simple abnormal karyotype, including things like T1517s and version 16s, etc. 21% complex, 4% with hyperdiploidy, 4% were inconclusive, and 6% were failures. Interestingly, moving across to OGM, you can see that our inconclusive and our failure rate actually dropped to 0% for all of the samples in this cohort. And so that was an interesting finding. One of the other interesting findings was our hyperdiploidy case. Half of these cases actually got reassigned because they fell into another category. So one of these cases, in fact, had a cryptic KMT2A insertion that we hadn't seen. So there's actually a few of those cryptic KMT2A rearrangements that were reassigned based on detecting with OGM. Other abnormalities that were detected that weren't detected in by classical cytogenetics were partial tandem duplications of KMT2A. We also detected B core deletions, RUNX1 deletions, MECOM rearrangements, and several new 98 arrangements that are quite often cryptic. And so, again, this is sort of where we're seeing a lot of that extra value in doing OGM because we're getting a more accurate classification. We're using the region file. So I want to talk very briefly about that as well. So after evaluating large structural variation and copy number abnormalities, we use the region-specific filtering to target SVs for reporting. And so what we really want to do is we want to detect those tier 1 and tier 2 biomarkers, especially in the context of a complex genome. And so we tested two approaches. One approach was using a pan-cancer region file. And the pan-cancer file that we have has 1,044 cancer genes that have a cancer association. And that's what we started with, is just sort of a general region file that gave us all the sort of genes that were associated with with cancer in some way. And then we decided that we may want to tighten that up a lot because we were getting a lot of sort of VUS calls that we weren't really sure what they are. They maybe were genes that were important in, colon cancer or some other solid tumor, and we didn't really want to throw a lot of, SVs out that weren't particularly relevant to myeloid neoplasia. And so we developed a myeloid-specific region file that has, I believe it's 144 targets on it in total. And so how we did that basically is we took the guideline papers, so the most recent guideline papers that have targets for, so this is the WHO 5th edition, the Curie paper, the Arbor paper, and the Derner paper, which is the ELN guideline. So we took all of those genes that were basically tier 1 or tier 2 genes and added those to the list. And this included any gene that we sequence on the NGS panel. So we included all the potential fusion targets that were recurrent in tier 1, plus all of the NGS targets as well. Because there's more than one way, obviously, to inactivate a gene. You can inactivate it by a missense or nonsense mutation, but you can also inactivate it by completely deleting the whole thing. So we want to be sure that we have all of those targets in place. And so what we were able to show when we did the analysis of our cohort using the pan-cancer and the myeloid-specific region file is that when we went to only looking at the 144 targets in the myeloid region file as opposed to the pan-cancer file, we basically only eliminated what we considered tier 3 and tier 4 calls. So we had a very successful reduction in the need to look at, interpret, or report tier 3 and tier 4 abnormalities. And there was only one gene, in fact, that ended up landing in tier 2, and this was in fact a deletion of BRCA2. And so obviously there's some discussion about hereditary predisposition to leukemia here, and should we be adding a set of hereditary genes? It's also, I think, open for discussion. But most importantly, no tier 1 abnormalities were removed when we used this myeloid region filter. So I think that was a really important step. So we have this 144 target file that basically looks like this. We can upload a version of this into the Access software. Sorry, I said most of this already. We've included a few regions, so the MYC region, for example, is a 3 megabase region because MYC translocations are not precise at all. They have a huge range over which they can occur. And so, this is actually a very large region. So again, it's something that has to be interpreted with some caution, but there are a few regions that are like this. I think MYC is probably the most, is probably going to be the one that's going to have the largest region that we're aware of, but there are others, including genes in the FGFR family, so that might need slightly larger regions on them than just the gene itself. And then the other gene we included was CDKN2A. It's not a guideline target, but there is growing evidence that CDKN2A deletions may have some prognostic significance in myeloid leukemia. So again, it's something that we included for the sake of including it. And of course, we need to work towards some kind of nationally consolidated list with a set of default interpretations. Okay, and I see Jean has already replied to Lakshmi's question about nomenclature guidelines. Jean, we're all very excited for those to come out soon. So stay tuned. That I know it's done, and we're just trying to find a home for it. So okay, and I am getting to the end here. I just wanted to talk a little bit about how we do reporting. So we built basically tables. We have a fairly extensive Excel reporting system where we have prognostic and diagnostic fusions, MLNTK fusions, prognostic and diagnostic SVs, and prognostic and diagnostic cytogenetic events. And so basically, as we go through, we've just basically sort of defined all of these events, and we have sort of standardized comments for these as depending on what it is you have to report, there should be some kind of comment automatically built for these in our reporting template. And so I guess, just to finish off here, I wanted to say that it's, we've really shown this to be a versatile tool for SV detection on samples referred with an indication for leukemia. We've been able to demonstrate improved classification for OGM, especially against the new WHO Heme5 and ICC classifications. What I think we really need to do is get a working group together, nationally to talk about the myeloid region file. And I think that's something that we should maybe, maybe each lab should elect somebody to sit on a working group, as to not make the working group too large. But ideally, I think I'd like to distribute our myeloid file out to all of the labs and have everybody have their input. You know, if you guys think there should be additional regions and how we annotate them, and then work on sort of development of standard interpretations for everything. And the other thing, obviously, is that, you know, we have to start thinking about probably lymphoid region files, or regions files, or region files. I don't know exactly how to do this yet, because there is a fair amount of difference in the lymphoid files. The lymphoid genes of interest, depending on the disease. So I think that, you know, it's going to be important to, again, for us nationally, to discuss how we go about developing these region files and try to maintain some consensus among all of us how we're doing this, whether we want, say, a BALL, TLL region file, and then a lymphoma file, a CLL file, I don't know. So that's something we need to discuss. And I know many of you have been patiently awaiting the framework paper, and it is done. We are shopping it around. It was submitted to Blood and it was rejected already. So we're working our way down the list, but it should be out very, very soon. Hopefully by the end of the month, we should have that out for everybody to see as well. Okay, and that's it for me. So we'll go to some questions and discussion. Okay, what's next? So Nazim asked a question: would you use this bed file for a patient with a questionable myeloid diagnosis? Yeah, so, you know, that's a good point. Again, right now we don't have an alternative, you know, in terms of like what, depending on what the diagnosis was. The file that we do have as a backup, of course, is our pan-cancer file. So, you know, we can always, there is a significant reduction in the number of SVs that are shown after you use either the pan-cancer or the myeloid. We didn't show the reduction. I didn't show the reduction from just no region file to the pan-cancer file, which is probably something, you know, we should show, but there's a significant reduction in that step as well. So, I mean, in a case where the you know, the diagnosis was not determined or not clear, you know, you could easily use a pan-cancer region file to help kind of bring the list of possibilities down. The other filtering option that you can also do is you can take one of the gene tracks, and you can say, just show me abnormalities that overlap genes. So that's another possibility. Although, you know, the GenCode gene track has a lot of genes on it, so we haven't really tried that to know whether or not that works or not. So, anyways, I'm not 100% sure. There's certainly lots of options for doing that kind of filtering. Yeah, yes, thank you, Fleischer. The guideline paper was rejected. I was pretty sure Blood was going to reject it. It's also not the shortest paper in the world. It's topped out at over 50 pages of double-spaced text and figure legends and stuff. So it's a very long, very, very detailed paper. So I can imagine that, you know, there's some journals that just don't have the space to accommodate a paper of its size. So Lakshmi is asking, please explain the slide of tiers and criteria for putting a marker in that particular tier. Sorry, you mean a biomarker or a marker chromosome? Biomarker, right, gotcha. So these are the tiers. These are the same tiers that were proposed by Mikhail et al. For microarray analysis. So, for example, anything that is defined by disease-specific criteria, anything in the WHO, the ELN, anything in any of the guidelines is basically a tier 1A abnormality. So, you know, a deletion 5q is a tier 1 abnormality, but also, for example, a B core deletion, so mutated B core is a guideline disease-specific requirement or disease-specific criteria, so it would also be considered a tier 1A abnormality. I don't know that we're actually going to get into defining really between tier A and 1B. I mean, some of these ones, like for example, there's a whole list of genes that are in the Derner criteria, the Derner ELN paper, that don't have a known prognosis or a treatment response that have really high quality evidence. I mean, those could technically be characterized as tier 1B. So that's you know, this, we could sort of talk about how we want to do that or not. Tier 2, obviously, these are acquired variants observed in different neoplasms, but not specific to a particular tumor type. So, I mean, one of these would be like a CDKN2A deletion. So CDKN2A deletions seen across myeloid and lymphoid tumors. They're very common. They're seen in solid tumors as well. Homozygous deletions are known to have generally poor prognosis. But again, this isn't a guideline specific. This isn't a guideline specific gene, CDKN2 deletions in myeloid, for example. So tier 2. And then anything else that's acquired, basically, that we don't know what it is, tier 4, and then, sorry, tier 3. These are variants of no or not known significance. And these can even be, if you had an SV that overlaps a gene, but the mechanism is wrong. So let's say, for example, you've got a gene like ASXL1, and you've got an insertion somewhere around ASXL1, and you don't actually know what that insertion does to the expression of ASXL1. So you just want to say, oh, by the way, we have this tier 3 insertion of ASXL1, don't really know what it does. So that's the other area where you might actually want to use tier 3 potentially. And then tier 4, constitutionally benign. So generally, these would be things that you'd see at about a VAF of 0.5. They're going to be in everything. They're not going to be associated with cancer genes, etc. Sometimes actually sorting tier 3s and tier 4s out isn't super easy, but anyways, I hope that answers your question. Okay, moving on. Susan says, great idea about the working groups for region files. Would be helpful to have a standardized review and reporting approach that can be reviewed annually. Yep, totally agree. I think that's sort of part of the reason we have this community of practice, is to get together, talk about these things, and then go away and do some work on them, and then come back and hopefully, you know, present back to the group and say, this is the Canadian standard, etc. Or international standard. I don't know. I mean, that's maybe a little bit too ambitious, but certainly we should be able to. We should be able to get to a Canadian, some kind of Canadian agreed standard for a list. Melanie asks, how close to a gene does the breakpoint have to be in the OGM data for the software to flag it when using a bed file? Yes, so there is a setting in the software. It's called the precision settings, and the precision settings, you control them yourself. You can set them to whatever you want. We are using right now SV precision of 30 kilobases, and we are using CNV precision of 10 kilobases. We were initially using 10 and 10, but we found that with some of the sort of looser, non-precise breakpoints, especially with 8p11 myeloproliferative neoplasms and FGFR1 rearrangements, that sometimes the caller wouldn't pick up that particular call, that because it wasn't within the gene, it was just outside of the gene. So we really sort of thought, we need to give ourselves a margin of error. And I should also point out that in the current version of Access, there's a visualization bug that BioNano is in the works. They're trying to fix it, where if you have an interchromosomal rearrangement and you have one end that has a defined gene that's in your bed file and the other gene isn't, it won't actually show you that rearrangement in the surface plot, but it does show up in the variant list if you go into the genome browser. So again, it's a visualization bug, just to be aware of it. Again, most of the time when we're looking for these kinds of rearrangements, they're pretty obvious. So we just see them in the general, you look at the circus plot, you're like, oh, 8 something translocation, great. Okay. So again, precision is something we could also discuss at the national level. If, we could put a series of cases together with sort of looser translocation and try to figure out what the optimal level of precision is. I think we've got a pretty good number. And then of course there are exceptions like MIC, which you need a region file that's 3 megabases. So that's sort of where we are there. Flesher asked about working group for lymphoid at large. Would be interesting, would include ALL, B and T lymphomas extending to multiple myeloma. Yep, absolutely. I think we really need to start thinking about these because obviously, we're going to be moving in that direction. Certainly ALL, CLL, and multiple myeloma, although it's technically challenging. Amelie and Isabel from Rosemont Maisonneuve will be doing really amazing work there, and they're out in front leading the charge, I think, on getting myeloma to work on OGM. So I think that's something we need to start talking about soon. Yeah, so Nazim talks about when you talk about counting the acquired abnormalities, sometimes it's difficult to distinguish acquired versus germline abnormalities. Is there a way to distinguish them by OGM data? I mean, so to the same extent that there's a way to distinguish them on a karyotype, quite often when we're looking for constitutional abnormalities, they will have very high VAFs. They're going to be in every cell, basically. So that's one of the keys. So if you have a lot of, like, if you have defining abnormality, a driver like a T922, and it has a VAF of 0.25, and then you have a translocation 416 that doesn't involve any genes and has a VAF of 0.5, again, very, very likely that is a constitutional abnormality. But I think, what a lot of us do in that situation is we often request a peripheral blood from the patient and we PHA stimulate it, and we then do an analysis on the T cells for non-T cell disease to sort of say whether or not that particular abnormality is a constitutional abnormality or not. I think I don't think there's an exit at this time from that particular scenario. I think the nice thing about the OGM data, though, is that when you do have a translocation between 2 regions, is that you can see what's disrupted at the breakpoints, and I think that adds a lot of important knowledge in terms of when you're trying to make a guess about whether a particular rearrangement either is somatic, is going to have some kind of effect or not, or is potentially constitutional. So there is all of that to consider. Lots of good questions here. Yeah, and Flesher, there you basically said exactly what I said. Excellent. Great. Okay. Let's see. So Ashish says this is classification looks similar to AMP classification of mutations. Hence, yeah. So again, this was one of the big focuses that we had in the framework paper when we sort of modeled this classification system, is that we wanted it to be very close to the microarray system and very close to the ASCO-CAP system, so that no matter what platform and technology you're using the same language to describe the variants. We think that's really important. We really want to not have, one of the things is, you don't want to have to change gears every time you change technologies. Sometimes we report a lot of this stuff, at the same time, you're reporting different technologies in the same lab, the same scientists. So, ideally, as much as we can make the criteria uniform across the different types, that's the way to do that. So I think that was that is the sort of the general philosophy behind it. So, yeah, Isabel, it's a good point about the tier system. And, I mean, again, it's not that we're using the tier system in absence of some kind of text description of what's going on. And I think clinicians are actually very familiar with the canonical, the guideline reporting requirements and the guideline SVs as they are. I think where the gap is going to be for a lot of clinicians is going to be when we get below cytogenetic, sort of classic cytogenetic size into the submicroscopic, and we start talking about, I've got a submicroscopic deletion of B core, and they're going to be like, okay, well, what does that mean? Is that a mutation? Is that and I think you're right. I think we need to get out in front of this. So I've been talking with Andre Shu from CLSG about doing a presentation, like an hour and a half presentation for clinicians specifically on that topic. And I think we all need to do more. I think if I'm happy to develop a set of slides for that talk and share those slides with other cytogenetic directors if they want to give talks in their own institutions to their own clinicians, sort of about how we go about doing this. I think that's we need to get that message out, and I'm happy that everybody can participate in that. Luke Richard asked, did you see or did you get any FLT3 ITD with OGM during your validation? So the FLT3 ITD is actually quite small. It's below the current resolution of the rare variant assembly. The lower end of the rare variant assembly for being able to detect structural variants is 5,000 bases. So the ITDs are generally smaller than that. I can't remember the exact size, but the standard ones are 40 to 80 base pairs or something like that. And they can be a little bit larger, but generally too small for OGM to detect. However, we are seeing KMT2A partial tandem duplications, which tend to be in the sort of 20 to 50,000 base pair size range. So, you win some, you lose some. So that's what we got. Great. Okay, I don't want to take up all the time. We've got some cases to get through, and I do want to give some time to go through some different cases. So I am going to take a back seat here and allow some of the other presenters today to present their cases. So Isabel, if you are ready, do you want to share your case? And Isabel is going to be talking about OGM analysis of a non-diploid myeloma sample, which I think is very exciting.
Okay, thank you very much. Please let me know if you can't hear me or if you can't. I'm hoping that you can see my screen. Can you see my slides? Yes?
I can see your file explorer.
Oh, so maybe that's not right if I do this.
Yep, that's perfect.
Okay. Great. So I'm hoping I'm going to try to not take up too much time because I know there's a few presentations. But I'm going to talk about a myeloma sample and a myeloma case, and they're not necessarily the easiest. So I'm going to try and explain it a little bit, but then also not take up too much of your time. So this is an example you can see on the left of a surface plot of a myeloma case that we have in the lab. And so you can see a number of things happening. Maybe the first important thing to notice is that we have a classical 1420 translocation, but you'll notice there's other things happening also. And if we zoom in on chromosome 1 here, we can see in the 1p region here, what looks to be a 1p deletion. If we look at our average number, we have 1.72 copies, fractional copy number. And then if we look on chromosome 1q, it looks like there's a lot of stuff happening. Maybe it looks like some chromotripsis or lots of events happening in 1q. And for, I don't know if I can do this, yeah. And for the gene CKS1B for 1q amplification or gain, it looks like we have a gain with a fractional copy number of 2.55. When you zoom into the 1q region here, you can see that even though there's lots of events happening for the gene, where the gene itself is situated, it would be considered a gain. So the software gives us a gain of 2.55. The interesting thing, however, with this case is when we compare FISH and OGM data, we don't really see the same thing. And I can't, oops. Oh, here we go. Okay, so when you look on the left side here, you have the FISH analysis. So you can see there are lots of different copies of these genes that we're picking up with FISH probes. So we've got 2, 3, 4, 5 copies of TP53. We've got 2 to 3 copies of FGFR3 and so on. When we go down to 1P and 1Q, which is maybe especially interesting and pertinent for myeloma, we can see we've got 2 and 3 copies of 1P, and we've got 2, 3, 4, 5 copies of 1Q. So we have 1Q amplification. But by OGM, you'll notice, as I mentioned with these two, that it actually, the software calls a deletion of 1P, and it calls only, it sees a gain, but not an amplification of 1Q. And you can see other discrepancies when you compare to the FISH data. And the main reason for this is because this is not a diploid genome, but unfortunately, OGM is not capable of seeing that it's a non-diploid genome. It's either a 3N or 4N or potentially a triploid genome. But unfortunately, what OGM does is it normalizes the non-diploid state to a diploid state, and then it gives calls relative to this diploid state that it has created. So there is actually a loss of 1P and a gain of 1Q relative to the non-diploid state, but it's not there is more than one copy of 1P. So it's not a single copy of 1P, and it ends up being an amplification. I don't know if I'm doing the best job of explaining it, but if you look at this whole genome view here, when looking at chromosome 1, you can actually change these values to be what is actually happening. So instead of being between 1 and 2, you're actually between 2 and 3. And so here you've actually got 4, 5, 6 copies of your 1Q, and in your CKS1B region, you've actually got between 3 and 4 copies. So you're more in an amplification state. But unfortunately, the software normalizes everything to 2N, and so it gives you these calls. So this is the main issue that we're facing with myeloma. So it's been actually quite incredible, OGM with myeloma, in terms of everything that it can show us, everything that we can see, everything that we can learn in terms of the whole genome. But these non-diploid cases are definitely tricky. And I saw a question pop up in the little chat about, do you ever run de novo analysis? And so one of the things that we try to do with myeloma is to run some de novo analysis, because in de novo analysis, we have these VAF tracks, which you see here in pink at the bottom. And so they actually represent allele frequencies. And so a normal diploid genome would actually have 0.5. So it would be sort of like this line here, where you would see one of each allele, and so you're sitting at one of each, and you're sitting at 0.5. When we have triploid genomes, we actually see these show up on de novo as these, when we look at chromosomes that don't have too many calls or SVs or CNVs, we can actually see that they split because we have an unequal allelic frequency because we've got triploid genomes with 3 alleles. And so sometimes you can actually spot this when you do your de novo analysis, but it can be very tricky. And when we run it on these are 2 example triploid genomes that we have, but when we try doing this with our genome, our sample that I'm discussing, you can see that we don't really see evidence for that. So maybe it's a tetraploid. Maybe what happens is there's just too many copy number gains and losses that it's not able to really give us evidence of triploidy when we do the de novo analysis. So that's about it. It's just a slight hint, and hopefully I haven't confused people too much, but it's definitely the main thing that we're looking at now to try to see how to approach cases like this, because we don't want to have false positives and false negatives. So I think that just sort of says what I just said, that that's an issue, how to conclusively recognize these non-diploid states, especially even number states that we won't see with de novo analysis. And we know that tetraploid genomes in myeloma are about 6 to 10% of cases, so it's not insignificant. And we want to limit the number of false positives and false negatives that we have. So I think that's it. Thank you very much.
Fantastic, Isabel. I think there's one point that I would make there is that you detected a T1420, right?
Yes.
So that's your primary driver, right?
Yes.
And I would shoot out to everybody on the chat, how many people are actually fishing for that rearrangement right now?
We do, but I
do
think you're right. We do, but I think you're right. There's probably a lot of places that don't.
Yeah. So I mean, I think that's the issue too. And I think the other issue is with the secondary IGH rearrangements, where you get the IGH break apart positive signal and you don't really know what's going on with the IGH. And so I think there's a lot of opportunity to sort of sort that out. And again, I'm not, I guess my thought is I think there's going to be a lot of evolution in the way we think about myeloma with new tools, because I think the ploidy thing might become less important as we sort of move to a whole genome assessment where we're like, okay, we've identified a complex karyotype in myeloma. We know that's a really important issue. And so, if whether or not we have, a really accurate assessment of ploidy is maybe sort of a secondary question. And then I don't know, because we sort of we've been thinking about this for BALL as well, is that, in probably 60 to 70% of BALL, frontline OGM gives you your answer and you don't care about the ploidy status. But then there's maybe another 30% of cases where we might run a very limited karyotype where we say we just count 20 metaphases to make sure there's no weird ploidy states going on or something like that. And maybe for myeloma, maybe there's something like that as well. Maybe we just have a set of centromere probes and we just throw them on a slide and do a couple of fish and you sort out the ploidy for a certain percentage of cases where there's no satisfactory ability to assign a driver. So anyway, we're obviously going to have to get together in this because there's a lot to talk about it, how we're going to approach it. So very exciting. Any other questions for Isabel?
I noticed that someone asked, is plasma cell enrichment? This was on CD138 positive cells, selected cells.
Yeah, there was a presentation this May at the GLGC. Sam Brody from Boston presented very, very preliminary data on using a 1000x coverage genome to do myeloma, which is another possibility. So the real question is, like, what are the relative analytical sensitivities of those approaches? And I think there's a lot of open questions technically. So again, I think there's lots of work to be done in this space. And, hopefully we'll hear a lot more from Isabel and Amelie in the meetings to come as we broach some of these really interesting topics. Okay.
Yeah. I should say that is also where we're at right now, is something similar to what you suggest, which is that for most cases we'll probably be okay, but then there'll be some cases where we'll have to do an extra fish to just make sure that we're not in a non-diploid state.
Yeah. I mean, an OGM and 1 fish is probably better than 10 fish.
Yes, I agree.
Awesome. Okay. Thank you, Isabel.
Thank you.
I'm going to call on my good friend Eric McGinnis to come to the stage, as it were, virtually. And he is going to present for us this afternoon cryptic driver rearrangements in 2 acute leukemias. And Eric, it's all yours.
Great. Thanks, Adam. Is that showing up?
Yep, I can see it. You're good.
Great.
Yeah.
So thanks. I have, we've been testing out OGM for around a year now, and we have a good number of acute leukemias we tested, and a lot of interesting cases they could show, but picked a couple simpler ones that I think are really informative to how much this can change practice. So I think, like Adam, we saw in our cohort, about 10% of AMLs had a change in prognostic risk stratification or diagnostic criteria with OGM. So I'll show you 2 of those, and then one interesting finding that I thought was cool to look at. So let me, there we go. So this person that I'm gonna show you first is an older gentleman with AML with prominent dysplasia in his red cells, and his current standard of care karyotype showed a loss of 3, a loss of 7, a loss of 17, and a marker chromosome, which looks kind of the same size as a 3. But he had a cytogenetic diagnosis of AML with malodysplasia-related changes, essentially, and he was started on chemotherapy for this. Came back with a sequencing panel showing some other bad mutations like P53, and had the same diagnosis stick. So for this patient, we had an OGM sample and tested it out, and as you can see, we pick up the things we expect to see. So there's a loss of 7, loss of 17, which is involved in some complex rearrangements of 3. So the 3 is not lost as expected. It's probably part of this marker chromosome here and just not really recognizable. There's also a little bit of involvement of 12, which isn't obvious from where we are. The interesting thing about this case is, sure, we picked up the things we knew were there. And if you go closer, you can see what these rearrangements look like. 3 is clearly a complex rearrangement that it's not recognizable as such. 17 the same. There's actually a little focal deletion here, which I think can come as P53. But the interesting thing here is there's a translocation that obviously we didn't see because we didn't know this is a 3. That involves chromosome 21. And if you look at the variant call here, this is actually a MECOM RUNX1 fusion. So this is the assembled molecule indicator here. This at the top is the reference 21, and you can see this maps to RUNX1. And this is the reference 3, and it maps to a region telomeric to MECOM, which breakpoints telomeric to MECOM are fairly common in these MECOM rearrangements. Looking below that, you can see this is the genome browser on chromosome 3, where you see the 2 translocation calls, telomeric to MECOM, and then on chromosome 21, you see these breaking into RUNX1. So this person, I mean, has bad prognosis disease either way, but this is a change from AML with malodysplasia changes to AML with MECOM rearrangement. And these MECOM rearranged AMLs, particularly in the context of chromosome 7 losses, tend to behave very badly. So in the end, I mean, this person didn't do well either way, but it does change how we would stratify this person and how they would be diagnosed. Next patient is one of these ALLs where we do the whole workup and find nothing. So another 60-year-old or so woman with B lymphoblastic leukemia, karyotype totally failed. We have no chromosomes to look at. We did our full fish panel. It's about 9 rearrangements to look for with, I think, 11 or so probes, and found nothing. So this person was given a diagnosis of B lymphoblastic leukemia and OS, and kind of went on their way with chemotherapy, standard of care. This is the circus plot, and you can see there's no big translocations, nothing immediately standing out as an obvious change that we'd go, oh yeah, that's what's driving it. We've had a couple of these where you see a subtelomeric translocation 1411 driving these, but nothing here being called. And this is actually just filtered on population filters, around 30 or so variants. If you filter this further, using B lymphoblastic leukemia specific gene set, it actually pulls it down to 1 variant, which is nice to look at, and it's this guy here on the end of 9q, which, as you know, is where ABL1 lives. So this is a view of 9q. You can see there's this duplication call where you have a copy number gain in the end of ABL1 spanning through to NUP214, and it's actually duplicated in tandem, fusing NUP214 to the end of ABL1. This is just another view of that same call where it's been realigned to show you that this is where ABL1 breaks. So this person actually has a targetable fusion that we were not able to see with our current standard of care testing, and would be given a diagnosis of B lymphoblastic leukemia, BCR ABL1-like, and probably eligible for TKI based on this. Seems like they've done relatively well so far, but if we have this knowledge at the get-go, they may have had options for other treatments than just standard of care chemotherapy. So I showed you these two interesting ones. One other one that isn't, a cryptic finding or anything, but I think this need to look at. This is a person with Leaf-Romani syndrome and came in with therapy-related AML. And on her karyotype metaphases, you see all these little double minute chromosomes that, if we fish, these are make amplification. And I always kind of, since we got OGM, I wondered what would double minutes with gene amplification look like on OGM, and we finally got one. So you see all these extra copies of MYC on fish. If you run these through the OGM assay, this is the copy number track for chromosome 8, and you can see here, baseline all across 8 until you get to the region of NIC. And this fractional copy state's around 16. I don't know if there's a ceiling for OGM, what it looks like. It's not something I've come across before, but this is kind of off scale. And when you look at the actual locus, you can see this is what this is how OGM sees double minute chromosomes. So this is horribly complex, a whole bunch of look at that. Adam said you can change the scale in the view settings. So I'm gonna try that out after the meeting and see how high will it go. So this is how it sees double minutes. You see a whole bunch of deletion calls where things have come together that shouldn't be together. You see a whole bunch of duplication calls where things are duplicated in tandem. And in the end, these are all probably just different fragments that OGM is trying to map and make sense of it, but it obviously doesn't really have a way to do that in a meaningful way other than this horrible complexity. So in the end, this person didn't have any identifiable drivers that we didn't see. They just have this neat finding of NIC on double minutes in OGM. So those are the cases I wanted to show. Just to tell you, our experience with Adam was similar. We had about 10% AMLs newly diagnosed, or changed prognosis, and about 30% of ALLs had, potentially meaningful cryptic findings. The ALLs tend to be very complex and have a lot of recurrent deletions. The one thing I wanted to add was that the lymphoblastic leukemias, we have encountered issues with ploidy, as was mentioned in the last presentation, where like a haploidiploid masked ALL was totally not called with any meaningful events on copy number losses. So we're not sure how to approach those cases. So going back to the question, sorry, I just popped the chat up here. I see Adams mentioned the rearrangement partner. Yeah, it was an NUP214, which is, again, we didn't rearrange with a couple other genes in our cohort so far. The reason it wasn't called as an intrachromosomal fusion, I think, relates to the size. So it has to be above a certain size threshold for it to be called as a fusion. And this is actually spanned, it's quite close together. As you can see, it's 130.8 mega to 131.2 mega. So it's, it's less than a megabase in size. So I don't recall what the threshold for this to actually decide it's going to call an intrachromosomal fusion is, but it's certainly bigger than this. So these smaller ones tend to get called as duplications or split duplications if they are. Adams, yeah, I think 5 is what I had in my mind as well. So if they're very small, they show up as smaller events like this, like the KMT2A partial tender duplications just show up as insertions and it doesn't quite know what to make of them. It just shows extra maps. These split duplications, you've seen a couple of them where if it's close enough together on the chromosome, it doesn't call it as a different interchromosomal fusion event. It calls it as a smaller rearrangement. So you have to go looking carefully for those ones because it's easy to look at the pink lines and say there's a big critical event there. But for example, we've seen a PDGFR beta inserted duplication of a similar magnitude that was again disease defining and the driver mutation, but that would have been was just called in the same way. Those are the cases I had. Any other questions on those?
Fantastic, Eric. I think we definitely need to get together on these region files. Figure out what we're going to do.
Yes. Let's stop sharing.
Yeah. Okay. Thanks, Eric. I think that was it for.
Sorry, I see there's a question from
one more question.
Ashish here. Able one up to inform TLL followed by amplifications. No, this case was it was very simple. It was a simple just the duplication. That was the only real relevant abnormality that we saw.
Okay, I think we're down to the last case, which is my colleague Rosemary Tremblay-Lemay and myself. So I'm going to throw up the case, and I will let Rosemary get us started. Let's see how I do that here.
So do you want to just so we're just presenting a case of mantle cell lymphoma with a cryptic IGH CCND1 rearrangement. So it's a 70-year-old male who presented with rapidly progressing B symptoms and transaminitis, was found to have extensive lymphadenopathy, spleen involvement, peripheral blood involvements, like mental and peritoneal involvement. There was a first bone marrow biopsy that was done in an external institution that raised the possibility of mantle cell lymphoma, but FISH had been negative for the IGH CCND1 rearrangement. And so the patient was then transferred to UHN for further treatment. And there was a repeat bone marrow biopsy that was done, mainly because of the transaminitis. I think they were concerned there might be concurrent hemophagocytic lymphohistiocytosis and potentially transformation. So the marrow was repeated for that purpose. And just very quickly, basically the patient had lymphocytosis with significant number of abnormal lymphocytes. And just to very quickly show, like you can see there's a lot of smudge cells, a lot of atypical cells, and just to get a sense of the size, you can have a neutrophil. In the second image, you have a neutrophil and like kind of smaller, more normal lymphs, and then you have these very large, kind of irregular, atypical lymphoid cells. Yeah. And these are the aspirate smears. And again, you see like very extensive involvement by those atypical lymphoid cells. And again, you can sort of see occasional neutrophils and erythroid cells just to give a sense that these atypical cells were quite large and pleomorphic. And the core biopsy showed extensive involvement. I think you can show the next one with the immunophenotype. And basically, flow cytometry had also been performed. I didn't put all the details just in the interest of time, but it was a very typical mantle cell lymphoma phenotype. And even though the cells were rather large, they were expressing B cell markers, CD5. There was very strong diffuse cyclin D1. And sometimes you can see a little bit of cyclin D1 expression in diffuse large B cell, but this was a level that was just way too much, and basically in keeping with the mantle cell lymphoma. Ki67 was high. And so based on morphology and immunophenotype, I had initially signed it out as kind of extensive involvement by the pleomorphic variant of mantle cell lymphoma. But knowing that the external fish had been negative for the rearrangement, I just activated a bit more ancillary testing, and I will let Adam go into that.
Thanks, Rosemary. Yeah, so just sort of briefly to talk about those results, we did perform MIC fish testing and TP53 fish testing. So you can see the MIC result on the left. It's a break apart probe, obviously not showing a rearrangement pattern. It's all normal. And again, the same for the TP53 results, showing no loss of TP53. This is also the result of the CCND1 IGH dual fusion probe. Not the prettiest. I believe this was a paraffinized sample that we did this on. So, anyways, it was no evidence again of positivity for CCND1 IGH using the Abbott IGH CCND1 XT dual fusion probe. Do you want to talk about I think we basically covered this, right, Rosemary?
Yeah, I think the only other thing is we did the mutation testing for TP53 and it was positive.
Yeah.
But other than that, I think that's where we were at that point.
Yeah. So we actually were lucky in this case. We'd had a couple of other samples come in as a result. So the lymph node biopsy, which had comparable morphology and immunophenotype, also negative for IGH-CCND1 rearrangement. And we were able to get, rather serendipitously, a pleural fluid that was fairly heavily involved with this lymphoma that was consistent with what was previously described. And we were actually able to get this sample and into the lab, and it worked, where we did a DNA extraction and we were able to do optical genome mapping. And so that was the result. So we had a relatively complex genome, which was a little bit surprising. And of course, there actually isn't an overt 1114, which, you know, we actually were not surprised at all that there wasn't one. So again, if you were looking for one, you'd be looking somewhere in here, going over here. And so, you know, we were, okay, well, what is it if it's not 1114? One of the translocations I will point out actually is this one. There's a T719. This may actually be a constitutional rearrangement, as a relatively high VAF, and it's much higher than the VAFs of all of the other rearrangements that are sort of between 0.04 and 0. Sorry, that should be 0.27, not 0.027. But you know, again, we had a couple of chromosomal losses, and if you look here, this is actually the region where CCND1 is, and then there is this translocation, this 211 translocation, and then there's this translocation over here, which is in the region of IGH, and there's this 214 translocation. So we've got these two translocations that share this breakpoint on 2, basically. So there's that one, there's this one, and the shared breakpoint. Okay, so these are the maps basically for these two rearrangements. So this is the 214, and you've got the TRAF31P1 gene on chromosome 2 as the overlap gene on chromosome 2, and IGH, the region generally on chromosome 14. There's a lot of little genes, obviously, that comprise the IGH cluster. And so that's the 214, and then here's the 211. And so it was just so highly suspicious to me that we would have these two rearrangements together, that one would have IGH as the partner, and the other basically breaks just distal to CCND1. It's just an ever so slight So this kept me up pretty much all night one night, trying to figure out what was going on. VAF of these two rearrangements is actually relatively comparable at 0.13 and 0.19, or alternatively in 0.26, 26% of the sample or 38% of the sample. And again, you'll note that there are these little purple regions in the middle of the breakpoints. And these are, of course, regions that don't map to either reference in the alignment of the hybrid map. So what do we do in these situations? All right, here we go. It's time for arts and crafts. So we get out our scissors and our glue, at least hypothetically speaking, and we start putting maps together. And so this just, I'll point out 4821, 4842. These are the two maps here. I actually got them aligned on the same on the same screen, which you can do if you play around using the show all button. And what I was able to do was I was able to align this map, the 4842 map, that is the rearrangements between chromosome 14 and chromosome 2. And it actually shows a region that maps perfectly back to chromosome 11. So you can see this rearrangement. So what's happened here is this is exactly where the CCND1 gene is, right in this region here. And it is approximately a 25 to 40 kilobase region where CCND1 appears to have been spliced in between the IGH region on chromosome 14 and this other region on chromosome 2. So it's basically an insertion of CCND1 chromosome 11 into the 214 translocation. So quite an interesting rearrangement. And I say, it's arts and crafts because this particular region here is actually below the thresholds in terms of size for OGM to be able to call it individually. You can do these alignments manually, obviously. And I put here for comparison as well, exactly, or more or less exactly, as best I could figure out from Abbott's probe maps, where the CCND1 probe sits and why we didn't see an abnormal signal pattern. And of course, for very, very small displacements of probe, anything usually below about 40 kb is very, very difficult to see by fish. And so it's just too small, basically. So this is a cryptic insertion of CCND1 into chromosome 14. So I thought that was really interesting. Now, of course, it's not finished there because remember that MIC was also negative, and there's the fish to prove it. You will recall that there is in fact an 814 as well. So there's the 8, and there it goes right there into 14. So if we go back to that, this was really interesting. The 814 is a very low VAF. It's 0.07. So my thought is that maybe this is subclonal. And I think that maybe correlates well with the fact that the IHC for MIC was patchy and that it might be in just a subset of cells and not all of them. So, again, there's something to think about there. Here's the IGH region on the bottom. So this is the ref for chromosome 14. So IGH, the enhancer region for IGH would be up in this region somewhere. And MIC is actually way the heck down here. So this is an extremely proximal breakpoint for MIC. The red probe for MIC would be in this region here. It would not extend all the way up to this breakpoint. So again, I kind of think where are the outer limits sort of for MYC rearrangements, and maybe, we know that the MYC break probe has some level of false positive, for a variety of different regions, more complex structural rearrangements and cryptic insertions and stuff like that, but also possibly because some of these breakpoints are way the heck out on the proximal side. And so this is our MYC region file. So remember, I was talking about our myeloid region file. This is where we sort of put the sort of proximal endpoint, which was not a bad guess, I guess, all in all. So anyways, I just, again, I think like sort of setting the endpoints of these region files is a bit of a tricky business. And these kinds of are interesting cases because they show where the potential endpoint is. And I'm, again, I think, it's hard based on how low the VAF is on this rearrangement to sort of really know, if this is truly driving MYC expression. But anyways, it's very interesting nonetheless. So I put that there for there. Okay, so that's that. So let me go. I see there's some questions in the chat. Let's see. So Ashish, I think I answered your question about can it be a three-way rearrangement. I think it's actually a little bit more complicated than that, but it is essentially the involvement of all those three regions in an insertion rearrangement. Let's see, Melanie. Melanie asks, is there a way to force the software to call this rearrangement differently? Like force it to call the CCND1 rearrangement, like force it to call the piece of CCND1. Yeah, so I think the problem is that piece of CCND1 is actually too small. It's sort of below the threshold where the software needs sort of a minimum number of labels on either side of the breakpoints of the rearrangement in order to be able to call it. I actually asked BioNano about this, and I said, what would be really fun to have is if like you had kind of like a label BLAT tool that you could say like, okay, I want to take this little like purple label piece and I want you to align it everywhere in the genome and then like give me a confidence score. So yeah, I don't know. I don't think they took me seriously when I suggested that, but that's just one thing. So anyways, so right now there isn't a way to force it to call that rearrangement differently. Amy asks, is there a way to confirm the IGH CCND1 fusion in this patient? Well, I mean, I think the confirmation is the high level of IHC staining for CCND1. I mean, it's definitely, CCND1 is definitely being driven. I certainly think we could, we could look at something like doing maybe using a long range sequencing platform to try to put the whole thing together and get it to identify. I don't know how well that would work because we haven't tried this kind of specific case. I know that it is calling SVs with multi-break fusions is still a bit of a complex task, so that might not be as easy as it sounds. So I mean, but there's probably a bunch of other ways we could go after it, but I still think it's pretty convincing with the data that we have. Nassim asks, in the case of insertion CCND1 to the 214, wouldn't you expect to see some molecules called as T1114? Oh, I think that's the same as Melanie's question. I think because that piece is just too small, there's not enough labels to actually align it to the reference. And so it's not making the 1114 call. Sorry, I didn't hear that.
और यहाँ पर जो है वो अभी तक एक दिलचस्प बात ये है
Sorry, I'm having real trouble hearing you. Like,
राजा रियाज साहब के पास वक्त नहीं था हालांकि दोनों शख्सियत मौजूद थी पार्लियामेंट में राजा रियाज साहब का भी शुक्रिया अदा किया असल में फरमाइशी शुक्रिया काफी और उसमें पीछे से नारे लग रहे थे कि आपने इनका नाम मेरा नाम या फिर उनका नाम लिखते थे या फिर दूसरे का नाम लेते थे किसी का नाम ये तो शुक्र है कि ये 85 रुपये का बिल है
sorry, I don't think that's. Yeah, I agree with you. Hold on, let me see if we can. There we go. Okay, muted. Yep. Great. Next question. Based on the size of IGH signal in the TLM14, can IGH break apart give some info? Yeah, I mean, I think IGH would show a break apart because you've got a 214. It just doesn't give you any, it doesn't really give you that extra piece of info that there's the CCND1 there. I mean, I suppose, I mean, if we were to use maybe very small probes, like oligo-based CCND1 probes with like a really strong labeling, like a branch DNA labeling or something like that, we might be able to really look at that rearrangement with fish. But anyways, okay, we're at 2:53, so we've got a couple of minutes left. I think that's all the presentations we had for today. I want to thank everybody that brought a presentation, for everybody your participation and asking lots of great questions. That was awesome discussion today, so I really appreciate that. I would like to get this sort of working group on the region files up and running. So maybe if everyone could maybe designate somebody at each center that would like to participate and send me an email. We'd like to kind of keep it a little bit lean, I think, to start with. So we have maybe one representative from each center that wants to participate. And I'm happy to share our region file and our interpretation and reporting templates to sort of get things started. So if people that are interested and that want to work together in a working group to sort of try to come up with a consensus region file and maybe even interpretation file, some description, certainly let me know, send me an email, and we can get that started with those that want to participate. Are there any other questions or any other comments? Okay, I think that's it. Looks good. I appreciate everybody. Don't forget to fill out the survey. And Anna, did you have any other additional comments at the end? No? Okay, great. Well, thanks everybody for participating, and we'll get another meeting set up in the next little while and send out a message to everyone. It'll be in about 3 months in November, probably. Okay, thanks everyone, and we'll see you all soon.